Okay, well, today I'd like to talk about Markov decision processes and reinforcement learning. And this is a little bit of a different kind of framing of a machine learning problem than we've seen so far in class. So mostly in class we've been looking at what I would call function approximation problems, trying to estimate some function from x to y, given examples of it. But today we're going to look at the problem of what some people would call control learning. So for example, imagine you have a robot like a helicopter, or a simulated robot roaming around in a grid world where it can be in one state or another. And all we want to do is have this robot learn a control strategy for choosing actions out of its vocabulary of actions, given the state that it finds itself currently in. And of course, to make that a well-formed problem, we have to say what its goal is and what it is that these actions are supposed to accomplish. So that's the setting for today. And this is yet another active area of machine learning. There are textbooks written on reinforcement learning and Markov decision processes. If you go to the machine learning conferences, you will find sessions on reinforcement learning and Markov decision processes. I have to tell you, one of the fun examples of this, well, reinforcement learning actually really works in practice. And one of the fun examples of this comes from a former undergraduate who took this very machine learning course in the 1990s. Andrew Ng is his name. He's currently a professor at Stanford. And as part of his thesis work, he worked on reinforcement learning and developed what turns out to be probably the most impressive helicopter control algorithm that exists. If you go onto YouTube and type in I don't know, machine learning helicopters or something like that, you'll be able to see the video and watch it do amazing acrobatic feats, aerobatic feats. But it turns out that's a problem of learning control, of learning to choose the right helicopter control action given the current state. And by repeatedly applying that control function, the helicopter gets to control itself. So there's one example. Another well-known example of this is in game playing. So if you think about playing a game like chess or checkers or backgammon or whatever your favorite game is, again, you're confronted with this question of, given the current state of the game, what action should I take next in order to optimize my chances of winning the game? That's actually what you're trying to optimize in that case. And in fact, in many games, including chess and backgammon, the best methods that are known are really based on machine learning and various forms of what we're going to talk about today, temporal difference learning. One well-known example of this is due to a guy named Jerry Tesaro at IBM, who was also involved in the Watson effort, by the way. But before he worked on Watson, Jerry was essentially the person who developed the first world-class backgammon playing program. And again, the way he did it was using reinforcement learning, the technique we're going to talk about today. And essentially his training signal was whether in the end the computer won or lost the game. And the experience that he trained from was hundreds of thousands of games that the computer played against different versions of itself. And then eventually it was able to learn a good control strategy, a good way of looking at the current board state and choosing the right action. In backgammon, I guess the board state is both where the pieces are plus what happens when you roll the die, what the state of the dice are also. So Now, if you think about this learning problem, you realize that it really is a little bit of a different kind of training experience that we're learning from. So it would be one thing if I asked you, how would you train a program if I give you training examples of the form, here's the board state, and here's the correct action, here's another board state and the correct action. Then you'd say, oh, we know how to do that. You're asking us to do another function approximation problem. We have a lot of methods for doing that, and you'd be right. But if instead I say to you, I can't give you that. If the training experience is playing games against yourself, then you never actually get a training example of the form, here's the board state, and here's the correct action. All you really get is training examples of the form, here's the board state, and I took this action, then my opponent took that, then I took this, then my opponent took that, then I took this, then I won. So what you get is this training data of the form, board state, action sequence, outcome. And so we're going to call this delayed reward for obvious reasons. And really the key technical challenge in doing this kind of control learning, reinforcement learning, is to figure out how can we design machine learning algorithms that can learn effectively from that kind of delayed reward, which obviously is not quite as informative as if we had a trainer saying, oh, in this position you should take this move. And that's really the problem at hand. If you think about it, most of what we do in real life has that character, right? Very few times, except when our parents are patiently teaching us what to do, very few times do we actually get training examples of the form, you're in this state, here's what you should be doing. Usually we just do a bunch of stuff and then we like it or don't in various ways. And so in some sense, this is the realistic wow. Okay, I vote we reinstall later. Oh, I see. We're going to get... Is there a way we can get rid of this? Okay, pay no attention to the man in the corner of the screen. What we're going to do instead is just forge ahead and ignore that. Okay, so here's the outline. We're going to talk about formalizing this problem of learning from delayed reward. We'll formalize that with a formulation that we call Markov decision processes, which has an interesting correspondence to hidden Markov models and Markov models in general. Then we'll talk about a couple of methods for learning that, and probably next time we'll talk about how recent research on animal learning has found that this is actually an intriguingly good explanation for a lot of work, a lot of observed data from animal learning. Okay, so here's the problem. In the abstract, we're going to think of it this way. We have some agent, that's the thing that has to learn a control strategy. It's in some environment, and what it can has some sensors that sense the state that it and the environment are in, plus it's going to get some reward signal. For example, in the case of playing backgammon, the reward signal is going to be 0 all the time, except if you win or lose the game, if you're in the final state. Maybe if you're in the final state and you win, we'll say the reward is plus 100. And if you're in the final state and you lose, we'll say the reward is minus 100. For every other state, the reward's going to be 0. We don't know what reward really to give. Okay, so it can sense the state and the reward. It can choose some actions. It has a set of actions to choose from. In the case of a game, these are the legal moves of the game. And so it's going to generate a sequence of states, then an action, then it'll observe some reward as a result of that state-action pair. And it will find itself in a new state, S1. It'll choose another action, get another reward, and so on. And then we're going to say the goal of the system is to learn a function that chooses actions. So basically, we want to learn a function that, given a state, chooses the action, such that we want the function out of all possible functions that maximizes this. What is this? This is just the sum of the rewards that the agent receives over time. And in the spirit of making immediate gratification a good thing, we're going to discount future rewards. So we're going to say, you know, if you have two strategies, one of which gives you a 0, a 100, and a 0, and the other one of which gives you a 0, 0, and a 100, we prefer the reward sooner than later, all other things being equal. Okay, so one way to think about this is in economics, or if you're investing money, people often talk about the current value of, or the future value of money. And so, you know, if I could give you $1 today or $1 tomorrow, you'd rather have it today. You can invest it, and it'll be worth more than $1 tomorrow. So you can think of this gamma as a coefficient. It's less than 1. It just means the same dollar tomorrow isn't worth quite as much as it is today. So you can think of that as roughly the interest rate in terms of money. Okay. So we're going to formulate the problem this way. And we want this to work for any reward function that anybody could ever make up, for any set of states and for any set of actions. Okay, so to be precise, here is what we mean by a Markov decision process. That's the framing of the problem when we say we're going to work on reinforcement learning. So again, we have a set of states, call those S, a set of actions, A, that's what the agent can do. And at each time, the agent is going to observe the state that it's currently in and choose an action. That's because it's going to have some function that it's learned, which takes it from a given state to its action. Then it receives the reward and ends up in a new state. Now, we'll call this a Markov decision process for a couple reasons, but one is that it makes the same Markov assumption that we talked about when we talked about HMMs. That is, we'll assume the probability that we end up in a particular state at time t plus 1, given our entire history, is really only dependent on the current state and the current action. So it's a Markov process in the sense that the future is independent of the past, given the present. Okay, we've talked about that before. We're also going to assume that the reward is Markov. The reward that we receive at any given point is a probabilistic function, but it only really depends on the current state and the current action. So when we make that winning move and put our opponent in checkmate, it doesn't really matter how we got there. It's putting them in checkmate. That's the thing the reward depends on. Okay, and so now the job is just to maximize the sum of these discounted rewards. But of course, if we assume that we have a non-deterministic world, where if I'm in some state as a robot and I command myself to go forward a meter, the actual outcome is going to not be exactly the same every time I try that. Right? It'll be kind of a meter, maybe a Gaussian distribution of points centered at a meter away. And so if we assume that we have a probabilistic next state function, then we can't really, it's more sensible to talk about maximizing the expected sum of discounted future rewards, since the function for giving us rewards is non-deterministic and the next state function is non-deterministic. Okay, so this expectation is really taken over, P of R given S and T, or S and A, and also over the probability of the next state given the current state and action. So over that distribution. Okay, so does that make sense? Okay, good. So here's our old friend, the hidden Markov model. And one easy way to digest Markov decision processes is to think about them as just a slight extension to this. So recall in the hidden Markov model, we said, well, we can go from one state to the next to the next. And in any given state, well, since we said these could be hidden states, there are certain features we'll observe at time t based on what state we're actually in at time t. And so now if we wanted to change this into a Bayes net for our Markov decision process, we have to add some more stuff, right? We have to add actions. So there's going to be also an action at time t. Oh, let's use a different color. Okay, so we could choose in, we could add in an action at time t. And now, what does the state at t plus 1 depend on? Well, it depends on both the state at time t and the action at time t. And of course, I'll have an action at t plus 1 and so forth. Okay. Now, we also have that reward thing going on. What does the reward at time t depend on? That depended on the action and the state at time t. So we're in state st, we take action at, we get some reward at that time, and then we end up in state t plus 1. Okay. So that's really it. So this is the Bayes net for a Markov decision process. Actually, to be more precise, what I've drawn here is a partially observable Markov decision process, because I'm assuming that those states are hidden. We can't exactly observe the state we're in. We only get to observe the O's. And just like in a hidden Markov model, here we wouldn't directly observe the states. We'd only observe the O's, which would give us some clues about what state we're in. So officially, this is a partially observed Markov decision process, affectionately known by the acronym POMDP. And sometimes you'll hear the acronym MDP for Markov decision process, meaning where we really can observe the states directly. Okay. Now, there's one thing I left out here, which is that function we're supposed to learn. Right, so how does that fit in here? So suppose, in fact, throughout here, I'm going to use standard notations. I'm going to use pi to mean the function that, given a state, we use to choose the current action. So I guess I would think of it this way. It's a volitional choice of the agent, so I'm not going to draw it as the same kind of arrow as I draw those other edges in the Bayes net. But basically, pi is the function that we have to learn, and that the agent will itself execute, given a particular state, to choose what action it should perform. And if, in fact, it's a partially observable Markov decision process, and it doesn't know exactly which state it's in, it just has a probability distribution over states, then pi will look at the probability distribution over states and pick what it thinks is the best action. Okay. So if we want to see the whole picture, I guess I would add a pi in here also. Okay. So now, again, given all the things that you know about Bayes nets, there are a lot of questions you can ask and answer here about, if you observe some of these variables, how to infer the others. If you needed to learn this, and you had fully observed data, you know exactly how you would learn it. If you had some partially observed data, you might be able to cook up some kind of EM scheme for doing that, and so forth. So I think this is a nice way. This is the big picture I carry around in my head for POMDPs. All right, and there it is, drawn a little bit more well. So now, in fact, what we're going to do is go through quickly two different kinds of algorithms. We'll start simple. We'll start simple with the assumption that the world is actually deterministic, not non-deterministic. So that if we're in some state and we take some action, we're going to deterministically end up in some next state. And we're going to deterministically get some reward. And then we'll bring in the non-determinism and see how we modify our algorithm accordingly. We're also going to assume that the state is fully observed. Actually, throughout today's lecture, we'll assume the state is fully observed. So this is a MDP, not a POMDP. Okay, and here's a simple example that I want to use to talk about some algorithms. So my notation is here. This is a world that a robot lives in. It has only 6 states, 6 positions in the room where the robot can be. And then what I've drawn here is this little state that has a G in it. You could think of that as the goal position that the robot is trying to get to. And the actions available to this robot are to move north, south, east, and west, the 4 possible directions on the grid. And its state is being in one of these 6 states. Okay, so now what I'm showing here, these arrows, of course, indicate what actions the robot can take from any given state. If it's in this state, it can either go this way, up, or west. And the little numbers that I've written on there, those are the reward function R. Okay. And you'll notice that I've set this up so that the robot gets a reward if it gets to the goal state and not otherwise. In fact, when I talk about reward, I'm going to try to be careful and talk about immediate reward. And that's what I'm showing you here. The immediate reward. If the robot's here and it goes this way, its immediate reward is 0 because it's not yet in the goal state. But of course, its future reward that it expects, if it knows this picture, is non-zero. And its discounted future reward is non-zero too. But its immediate reward, the training signal that it receives, R, is 0 everywhere except when it gets to the goal state. So this is just like the chess playing program that gets no reward until it puts me in checkmate. Okay, so there's a simple example.
So what exactly is the goal state?
Oh, I just made up that as a goal state. So I'm just considering a problem where the robot, its job is to get over there. Just so that we'd have something for it to learn. If I don't define a reward function, then there's sort of no meaning of learning. Uh-huh.
So in this diagram, you have the goals, well, one-way arrow into the goal state, but like in backgammon or chess, the goal state's going to be moving all around. And depending on where it is, there might be an in and out function, but you won't really know. It's not defined in a linear way like this. Really.
Right. So in backgammon, the goal state literally is to get all your pieces off the board. And there are many board positions that have that property. And so if we tried to make a different node here, a different grid square for each backgammon position, then you're pointing out, well, there will be many goal states, all the ones where my pieces are off the board. And that's okay. There's nothing here that says I have to make all these 0 except for 1. So I can put rewards on any of these state actions. Any function here will do. And so if I were doing it for backgammon, I'd define a reward of plus 100 for every board state in which when you take that action, you remove your final pieces.
So is it also possible to have negative rewards, like penalize it if you do something bad?
Right, so we can add negative rewards as well. Right. And in fact, part of the engineering, I mean, if you think about doing this for real with a robot, then you realize it's not trivial to make up the right reward function, right? Like if I ask you, what's your reward function? It's hard to write it down. And even if we want to do something simple, like give a reward function to a robot that was just going to roam around this room for the next month and never collide with things and never run out of power. When it got low, it should go charge itself in an outlet. So we think about that. Then we could think about making up reward functions. Well, if it has a collision, let's give it a negative reward. If the battery gets down to 5%, let's have it give an extremely negative reward. And if its battery is less than 20% and it feels itself plugged into the wall, let's give it a plus 1,000. So we might design that. But now you realize, as I start saying that, we don't know how to weight those different penalties and rewards and so forth. So engineering the reward function is kind of an interesting problem. And indeed, some of the really interesting research in this area right now has to do with reverse engineering reward functions. So there's a lot of research right now on allowing a human to teleoperate a robot and then having an algorithm figure out what is the reward function such that this person's actions are consistent with that reward function. And if you can estimate that reward function, then you can give it to the robot too and have it autonomously try to continue to improve that. So picking the reward function in general is an engineering problem and not straightforward. But for us, we're just going to consider this simple thing so that we can get to the heart of what are algorithms for learning pi, our control strategy, given a world like this. Okay, so let's go forward. Now, as we mentioned, one of the problems with learning this function pi from state to actions is we don't really have any training examples of that. The only training examples we have are state, action sequence, sequence of rewards. So, well,
It's just 4 hours, so we do the drop-down box.
The drop-down box, remind me.
how do I get rid of this?
Inside the Windows Update,
Remind me in.
the drop-down box. Not 10 minutes, but there you go.
That's going to be better. I don't know about the mass comparison guide. Wow. Okay. All right. So the way we're going to be able to learn this control strategy is that we're essentially going to learn an evaluation function over states. And let's call that V. In fact, what I can do is for any function pi, remember pi is our, we'll call it our policy function. That's the one that we use for choosing actions from states. For any pi that you want to define, I can define the value of being in any given state, assuming that you're going to follow control strategy pi. Why? Because we've already said what we're trying to do is maximize the expected sum over time of these rewards discounted by exponentially by gamma into the future. And so I can say, well, the value, just like, you know, having $1, if the interest rate is 5%, having $1.05 a year from now is worth the same as having $1 now, right? In the same sense, I can talk about what's the value of being in a particular state, assuming we're going to follow strategy pi, and its value being the sum over the infinite future of my expected rewards. So that's the evaluation function that we wish we knew. And if we had, let's say, a table where for every state that we could be in, somebody told us what the value of v pi was, then we would know, if pi is, let's say, for a robot grid world, always go east. Unless you can't, then go north. If that was our policy, pi, then we could label the value of each of those states by the sum of expected future rewards. Okay. And then we could choose over all the possible policies pi. We could say, well, we just want the one that maximizes the value, that value of states, and we want the one that maximizes for every state. Now, if you think carefully, it's at first not obvious that there could be a pi that would maximize the reward for simultaneously be the best pi for every single state in the world. But in fact, it is. So if you weren't worried about, continue not to worry about it. If you were, be reassured that there is such a policy. So such a policy does exist. I mean, it's one way to think of it is if there was policy 1, which was really good if you were on the left side of the world, and policy 2, which was the right one to follow if you're on the right side of the world, then what you could do is you could define policy 3, which says use policy 1 if you're on the left side of the world and use policy 2 if you're on the right side of the world. And then that policy 3 would be one that it achieves the optimal result from every initial state. Okay, so, and we'll call this best policy, pi star, and the value function associated with it we'll just abbreviate to v star. Okay, so v star is a precise definition of what's an evaluation function we wish we had. For example, if you're playing chess, there are a lot of board states. If we knew the value of being in every single state in terms of its expected future discounted reward, then any chess position, any state I'm in, I can just try out each of the possible legal moves, look one step forward, apply v star to see which of those is the best state, and out of those 27 possible next board positions, I'll pick the one with the highest v star. Okay. So just a standard evaluation function kind of thing. Yep.
So how, if with that kind of exponential decay for future reward, how do you avoid for long sequences getting, I guess, numeric underflow in the worst case scenario?
Yeah, the question is how do you deal with this infinite sequence and underflow issues and that sort of thing. In practice, that's usually not a big deal because we're only able to learn these functions approximately, and we can never go forward an infinite number of steps in time. And also the approximations to v star that we're going to learn in complicated worlds are usually approximations where the precision at the underflow level just doesn't come close to mattering. Okay, so there's the formal setting of the problem. And notice, as I said, if we know the next state function, even if it's non-deterministic, and we know this v star, then for any state, we know what we want, right? Pi star of, in any given state, is which action? I'll say it's the argmax over possible actions of what?
Expectation of the value function of the next space.
Right, so it's going to be the sum over states that the next state can be of the probability that state t plus 1 will actually be state S, given that state t is ST, and action is A. So it's a probability we'll end up in that next state times what? Times the value of being in that state, V star of S. Right? So it's just the expected value of V star I'm sorry, I have S here. I have to be careful. Let me make that an ST. Then all will be well. Okay, we're in state little st. Then we want to choose the action that maximizes the expected value of the next state we're going to be in. And that next state depends on the probability distribution on states at t plus 1, given the fact that we're in state little st and that we're choosing A. So then we want to choose the A that maximizes that value. Okay, and so in fact, I could have equally well written that just as the expected value of V star of I'll just use S prime to mean the state we actually end up in next. Okay? So, you know, if you've ever written a forward search, look ahead by one step program, you've got this concept. Okay, so now let me ask you, just to make sure we're all on the same page. If I define pi as this green policy, and I've defined it exactly so that in any one of these 6 states, there's exactly one action that pi recommends. It's the circled green one. And by the way, when we're in goal state G, there's only one action available, which is to sit still and remain in goal state G, for which we receive a reward of 0. But that's our only action available. Okay, so now if my discount factor gamma is 0.9, and again, we define the value this way, then what's the value? Well, first of all, what's the value of being in this state? 0. What's the value of being in this state? 100. What's the value of being in this state? What's V for being in this state? What's V pi for being in this state? Right, so if we're in V pi, or if we're in this state, and we follow V pi, or we follow pi, that means the green action, we're going to go this way. And then we're going to go this way. So we're going to receive a reward at time t of 0 from this state, because we're going to go here and get this 0. Then at t plus 1, our reward will be 100. And then we'll receive zeros in the infinite future after that by sitting still in state G. So then since our gamma is 0.9, that means this is worth 90. Right? The discounted future reward expected for being in this state, assuming we're following the green policy pi, is that we expect to receive 0 reward followed by a reward of 100, which will discount by our factor 0.9. 90. Okay, what's the value of being in this state? 81. What's the value of being in this state? Why is it 81? Why is it not 100? Right, because I'm asking for V pi, and I define pi. Unfortunately, this is a suboptimal policy that I have here. Instead of saying to go to the right, it's saying to go down if I'm in that state. Okay, so you see this value is dependent on what pi is. That's good, because what we're going to do is try to argmax over pi, the value function, at every state. Okay, what's the value of this state? 73. What's the value of this state? right, 66. So all I did was I just keep multiplying this by 0.9. In fact, honestly, when I calculated this, I didn't sum up 0 plus 0 plus 0 plus 0 plus 100 times gamma to the m. I just said, oh, if the value at 7 is 73 there, then a quicker way for me to compute it is just to say, well, v pi at this state is just v pi at that state times the discount factor, because I know I can get there in one state. I did a kind of dynamic programming. And that's the algorithm that we would use if we had this kind of setting. It's a dynamic programming algorithm, right? What's that?
It won't work if there are cycles on pi.
Yeah, we get into some trouble if there are cycles. Well, no, actually we don't. Let's make a cycle. Oh, yeah. Well, there's some subtleties if there are cycles. If our cycles involve 0 rewards, we quickly can find that out and kill the cycle.
It's like solving the matrix equation.
That's right. That's right. So if the cycles have 0 immediate rewards everywhere in them, then we can quickly see that we don't have to keep cycling. If they do, then maybe we have to solve some kind of infinite sequence problem. All right. Now that was the v pi policy, which we agreed was suboptimal. What's the optimal policy? Well, obviously, it's to go north if we're not yet north, and then to go east. So we never want to go south or west, basically, is the optimal policy. Okay, so under that policy, let's call that pi star the optimal policy, or abbreviate it to v star. What are the values for v star then? So what is v star at this state? Still 0. This one? 100. This one? 90. This one? 100. This one? 90. This one? 81. What's the optimal action if we're in this state? Doesn't really matter, right? We go north or east. Both of those give us next states whose expected future discounted reward is 90. So obviously it doesn't matter. Okay. All right. So this is the kind of function that we're trying to learn. And so now let's learn it. So essentially our learning algorithm is going to be a lot like dynamic programming. It's going to involve, and if we have a policy like that that doesn't have loops, we can just do dynamic programming. In fact, if we have a big state space, actually dynamic programming is not a bad idea. If we have policies that don't involve loops. In general, what we're going to do, though, is run through, if you think about what we're actually going to do is run through the world, taking random traces through the world, and doing dynamic programming like updates every time we take a step. So for example, if I'm in some state and I don't know what the v star value is, and I decide I'm going to go north, and I do, and now I'm in a state where I already have some estimate of what the v star value is, like maybe I think it's 0.8, then I'm going to update the v value for the state I was just in by saying, well, it's at least 0.8 times gamma. Or I'm going to estimate that as my estimate if my estimate of the new state is 0.8. And if I keep doing that, if you think about it, that's a dynamic programming kind of update. And if I do that enough, if I say hit every possible transition in my world, then I've effectively implemented dynamic programming. And so this way is just a way of sampling state action transitions. If you think about how you play chess, you don't actually start at all the possible checkmate positions and then back up and compute all of the possible one move away from checkmate positions and so forth. What you did, I bet, if you learned to play chess, was you just sampled some of the chess states. And you started noticing as you went forward that, oh, this is a good state to be in, or, oh, I just lost my queen, that's a bad state to be in. And then you kind of backed up, said, well, I guess I won't let my opponent put me in check and threaten my queen at the same time. That's probably a bad thing to do. So what you did, and what we're in fact advocating here, is just tracing through the state space, and every time you take a step, using our refined estimate of what the value is where we currently are to update our estimate that we used to have for where we were coming from. And the one reason we can do that is that this definition of V star actually has this nice recursive form. If you think about it, V star we defined as just the expected sum of discounted future rewards. Well, we can rewrite that as the reward at the first step, which is the expected reward from the current state and whatever action we choose in that current state, plus the sum of all those other terms, which, as we noticed when we were doing the calculation ourselves, is really just the discount factor times the expected value of the immediately next state, S prime. Okay, so let's look at that. That leads to the following simple algorithm. It's called value iteration. And here's the idea. We're just going to randomly roam around in the world. Could be random. And we're going to go until the policy is good enough. We can come back to what we mean by that. So for some state and for some action, we take that state action pair and we execute it. Now we observe some reward, R, for that state action pair. And in the new state that we're in, so S prime is the result of applying action A to state S. So then we look over all the possible next states and get the expectation of the values for the next state. And we'll call that quantity Q of a particular state action pair. And then for state S, we're just saying, well, we can take the maximum over those of the possible actions we could do in that state, and we'll just call that VS. Now, of course, when we do that, we don't really know V star. We just have, all we have is our own estimate of V star. And so V here is our own estimate, and we're updating V for state S based on our estimates of V for state S prime, plus, and here's where the thing comes in, the observed reward when we did that one transition from S using action A. So if we execute this enough, then our estimate VS will in fact converge to V star, because when we update V of S, we're taking the maximum over all the actions we could take from that state. Okay, so does this make sense? Okay, so let's execute it once just to make sure. Oops, I think I have a, I see. Let's execute it here. So actually, the way I've written it here, we can just pick arbitrary state actions pairs. And if our robot knows the next state function, if it, you know, if it's like a game and it knows that if I make this move, here's what the board will look like next, then indeed it can just randomly pick state action pairs. They don't even have to be connected, and just do this. And so, for example, if we start out with V as all zeros for every one of the 6 states, then if we start by picking this state and this action, we will end up with V still being 0 here. But if we happen to pick this state and this action, then we will notice that V here is actually worth 100. And if we later pick this state and this action, then we'll know that V here is actually worth at least 100 times gamma. And once we know this is worth 90, if we happen to pick this state action, then we'll notice this one's worth at least 81. And so one kind of unconstrained thing is just randomly pick state action pairs, apply them, do this update rule. And if we wait long enough, this will converge to V star. A different way to do it is to actually make our state action trajectories connected across states, the way you would if you played a chess game. You take an action, then your opponent takes an action, then you take another action, they're connected. And we could do it either way, so long as we visit every state action pair infinitely often, we'll be able to guarantee that we converge to V star. Okay. But so here's the property of that algorithm. So it does converge, but only if we visit every state action pair infinitely often. What do I mean by that? What I mean by that is, let's imagine we're sampling state action pairs. Could be by randomly choosing them or by following random paths through the world. And I'll call a full visit a certain amount of time during which I visit every state action pair in the world. I'll call that a full interval. And after that full interval is over, I visited every state action pair. To guarantee convergence, what I have to do is say that I will have an infinite sequence of full intervals. So I have to visit every state action pair and do it infinitely often. And that guarantees that no matter how far back I had to propagate those faraway rewards, I'll eventually succeed in propagating them far enough, because I'm visiting every state action pair again and again and again. And so there's a convergence proof that shows this will work. We'll see that proof in a sec, or a better proof than that in a sec. And so one of the nice implications of that is if our robot just randomly roams around through the world, as long as it roams forever, we know that it will eventually learn the V star function, as long as it doesn't get trapped in some corner or run out of battery and not be able to move anymore. Okay, so the theoretical guarantees on this are actually, I think, apply only to idealized situations. We're not really going to have physical robots that roam infinitely through the world an infinite number of times. But they help us understand the convergence properties of the algorithm. All right, and here's another interesting fact about this algorithm, this value iteration algorithm. If the maximum over states in the difference between two successive value function estimates, meaning before and after we do the update on that estimate for a particular state, is less than epsilon, then the value that we'll actually achieve if we follow the policy using this not quite correct V value differs from the reward we'd get from the optimal policy by a bounded amount, where gamma, again, is our discount factor and epsilon is the error in those estimates. So this result relates the error in our V star estimate and our discount factor to how much we would suffer if we actually follow this only approximately right policy. And so that's kind of an interesting result. Okay, so one reason I want to go through that kind of quickly is there's another whole half of this story, which is so far, if you think about applying that value iteration algorithm, we can only apply it, or our robot could only apply it, if it actually knows the next state function. Right? For example, even if it knows V star perfectly, it can't choose which chess move to make next unless it has the ability to predict what the state of the board will be if it makes that chess move. Because it's going to have to apply V star to that next state and this alternative next state and so forth and pick the right one. Now, in the case of chess, that's no problem because when we teach, if you want to have a computer learn to play chess, of course you would start by telling it the legal moves, and you'd consider learning means to learn to choose among those legal moves. But if it's a robot, it doesn't work as well because we can't tell the robot the next state function. You know, if it's a complicated robot with arms and legs and stuff, telling it to move forward 1 meter, we don't really know. But you can't write down the next state function. Or if we tell it to do this with its hand, or this with its hands, what will be the next state? We can't really tell it. So, in realistic problems, a lot of realistic problems, not all, backgammon doesn't suffer this problem. But in a lot of robot-like problems, we don't really know, our robot doesn't really know the next state function, the distribution on the time t given the previous state in action. So the puzzle is, and I think this is one of the coolest things about reinforcement learning, the puzzle is, how do we get our robot, which doesn't know this next state function, to learn a useful policy that it can actually execute, even though it may never know this next state function perfectly. And the idea, which you're going to appreciate, is called Q-learning, and it involves just a little tweak on what we were talking about. And here's the tweak. So before we were saying, let's define the value of a state to be the expected immediate reward we'll get if we're in that state and take the perfect policy. I'm going to erase those so you don't think they're primes. Plus gamma times the expected V star value of the next state. So what if instead I define this function Q, which I'm going to now define over state action pairs instead of states. And I'll say that Q is the same quantity. First, it's O, only it's a slightly different quantity. For action A, what we're going to do is we're going to say, we're going to use the expected value of applying action A to state S, plus the expected value of following the optimal policy from the state that we end up with after we apply A to state S. Okay? So you can think of it this way. The first line, V star of S, we're defining as essentially what's the value we will receive if we follow the optimal policy forward from state S forever. That's what V star is. Think of Q of SA as the following thing. It's what's the expected reward we receive if starting in state S, we first do action A, whether or not it's on the optimal policy. We're going to do action A. And thereafter, we're going to follow the optimal policy forever. So that's the Q function. It's almost V star. It's just it's follow the optimal policy right after you take action A in the current state. And by making this slight twist on things, we're going to be able to learn and execute Q, a policy based on Q, even though we don't know the next state function. So that's actually the beauty of Q learning. Okay, so how will we define our policy then? Our policy is just going to be, well, if we know Q, then of course we want to pick the action that is going to maximize Q. Because Q, again, is just the reward we're going to get immediately when we follow action A, and then the expected discounted reward of following the optimal policy thereafter. So of course we're going to want to execute the best A, the one that gives us the best total expected reward. And so that's how if we have Q, this is how we're going to choose our action. And notice there's this very simple relationship. The value of the current state is just the Q value that we get if we pick it's just the Q value of the best action that we can apply now. Okay? So you gotta get your head around this, but this little twist of going from V to Q opens up the possibility of learning these. We can now learn the Q function and then read the policy off the Q function this way. So let's take a look at. Here's a good big picture. So here's our grid world again. Here's the immediate rewards again. Here's the optimal policy down here. And here's the optimal value function, the V function we had talked about before. Here's the Q function that corresponds to that. So you see the Q function just has values for every state action transition instead of values for every state. But it does have the property, of course, that in any state that we're in, like this one, the V value is just the maximum over actions that we could execute of the Q value for that action. So in this state, the Q value tells us going north is worth 90, going this way is 90, this way is 72. Sure enough, the V star value is just the maximum over those three Q values. And so now if we can just learn Q, that's all we need. And learning Q is simple. Here's the idea. So as we said, Q and V star are related by this simple expression. And so we can write Q recursively by saying it's the reward we receive when we do action A plus the reward we'll receive if we follow the optimal policy thereafter, which is just either one of these quantities. We can write it either way. Oh, delta here, delta is the next state function.
So you don't know that one.
Pardon me?
So are you still considering the case when this function is known?
Ah, right, and that's precisely the point. So if we knew delta, of course, we could just learn V and do fine. If we don't know delta, the point is Q doesn't require delta. So we use the second expression instead.
Then what is ST plus 1 in the second equation?
That's the state that we end up in when we actually take action AT in the world. So now what we're going to do to train is we're actually going to use this rule, which is just the second expression. The robot will find itself in some state S. It will decide it's going to do action A. And since it doesn't have a simulation of the world that allows it to predict what the next state of the world will be if it does A, it's just going to do it. It moves, and oh, it bumped into something, minus 100. Okay, so the training rule is actually going to use the world as its own simulation. And so the training rule is, we're in state S, we take action A, we see what happens. Oh, we got a negative reward. Okay, now we know what the reward is. And now we know what state we're in. Here we are leaning against the table. But now we wonder, well, how good is this state? Well, we've got our current estimate of Q. And we apply our current estimate of Q to all the, we know what actions we can do now. We can go backwards, we can go sideways, we can go that way. So we take the max over those three actions of our current Q hat estimate. And then we say, okay, that quantity plus this minus reward that I just received is how I'm going to update my entry for the Q value for the state that I just came from and this action of going north.
Will this converge? It's like if you're in this state and the next state is probabilistic. So this time you go, it's very good. The next time you go, it's bad. So
right,
like
right. So is this still going to converge? And beautifully, the answer is under appropriate assumptions, which we'll see in a second. Yes, it will converge. So the beauty of this idea is we're actually letting the world be its own simulation. And of course, we couldn't do that if we were really doing strict dynamic programming where we had to cover every state methodically. But since we already noticed that even when we were talking about learning V star, in the case of a deterministic world, if we knew the next state function, we realized we wouldn't actually have to organize the dynamic computing computation methodically starting from the goal state and working backward. We could instead just sample. That was the whole point of value iteration. That sampling the state action transitions infinitely often, infinite number of times, would converge. And so once you get that idea, you realize, oh, I can use the world as its own simulation as long as I can sample the world infinitely often for an infinite number of times. And so that's actually the idea of Q learning. So let's go forward. So that leads to the following simple algorithm. So our robot finds itself in state S. It does this forever. It chooses one of the actions it can do in its current state. Now it's no longer able to just pick arbitrary SA pairs. It has to go with the state it's in. It executes that in the world, not in simulation, in the world itself, receives some reward, observes the new state it's in, and it updates according to the rule that we just said. And then we just do that forever. And of course, now it finds it's in state, this new state. Okay, so now when and under what conditions will this converge? Actually, let's just apply this once so we're sure we know what the algorithm is. So here's my robot. It happens to be in this state. And here are its estimates of the Q values for particular state action pairs that it has so far. And now it decides to execute the action of going right. And so now it finds itself in this new state. What's the update? Well, here's our update rule. Right? It just says what we're going to do is we're going to update the Q value for being in state 1 and going right. That's this arrow right here. That's the Q value entry we're going to update. It used to be 72. Now we're going to replace it by whatever reward we immediately received. Well, we didn't get any. That was 0. Plus gamma times whatever we think this state is worth, which is the maximum over all possible actions here. Well, that's 63, 81, 100. Okay, so the max of that is 100. So there's our update. So the robot takes just one step, and it updates the Q entry for the state action pair that it just executed. And now takes another step and does the same thing for that next state action pair. And you can see that if it could randomly sample state action pairs from the world, it'd be a very similar process to the value iteration we talked about before. In fact, since it's roaming through the world, it can't just do that. It's got to follow some trajectory of connected states and actions. And nevertheless, if that trajectory leads it through all the state action pairs, a full interval, an infinite number of times, then it will converge.
So doesn't it know now also the reverse arrows of fate values? Should you be, so the 63, should that be updated too?
So the question is there anything else we can update from this experience? No, not really. You asked, maybe we could update this one? Not really, because the problem is, if we don't know the next state function, we don't know what action, we don't know if we execute that action, which state we'll end up in, especially if it's non-deterministic. So in general, this is the only information we can squeeze out of the action. Okay, so so that's our yeah, let's do this. So here's the proof. I just want to go through it quickly. You can study it a little bit more in detail later if you're curious. But here's the proof that this Q-learning does in fact converge. And let's just go through it together. So we're going to use Q hat to represent our estimate of the true Q function. Again, the true Q function is the Q values for the optimal policy, but we don't know the optimal policy. That's what we're trying to learn. We can either learn the policy directly, or instead we could learn Q and then just calculate the policy from Q. And so what we want to show is that our estimate will converge to the correct Q value. And so let's consider the simplest case where we have a deterministic world. So it's not a non-deterministic, it's deterministic, but we don't know what the next state function is. And where we see each state action pair, we're doing this trajectory. We just happen to run forever in a way where we visit every state action pair in a full interval, and then we visit every state action pair again, and then we visit every state action pair again. So as I said, this is a slightly idealized robot life, but let's consider that case. Then, as I said, we'll define a full interval to be an interval during which we visit every state action pair. And let's say during each full interval, the largest error in the Q table is we're going to be able to show that it's reduced by a factor of gamma, which is our discount factor. When we take the sum of future discounted reward, it's gamma is the discount factor that we're using. So what we're going to show is that in each interval, each full interval, the worst error in our table of Q values for different state action pairs, we'll have a different error, of course, for every state action pair. If we pick the worst of those errors, the state action pair for which our Q hat is furthest from the truth, we're going to show that that worst error is reduced by a factor of gamma during each full interval of the robot's search. So let's let Qn be the table of all these. So I have state, action, Q hat. So I have this big table of states I can be in, and my Q hat values I'm going to write in. This is how I'm going to represent my function. Okay, so imagine that's the Q function I'm learning. So what I'm trying to show here is that secretly there's the real Q value, which of course our robot doesn't know. But if I look at the error for any given row in the table, what I'm claiming here is that I can reduce during each full interval of training the worst error by a factor of gamma. Okay, so let's let Qn be this table after n updates, and delta n be the maximum error that's currently in there. Maybe this is delta n right here. So it's just the max over all state action pairs of the difference between our estimate and the truth. And now, here's the proof. For any table entry updated on iteration n+1, we could say the error in the revised estimate is just, here's the revised estimate is Q of n+1. So its error, the difference between it and the truth, is just this is our update rule that we're going to use to update the Q entry for S. This is just the update rule we were just talking about. And here is the truth. Notice the only difference between these expressions is that our update rule has to use Q hat, whereas the truth depends on Q, which we don't know. So that's the error when we make our update. It's the updated value minus the truth. So now all I do is I can just cancel out these r's. It's r minus r, so that's no problem. And now I can just bring the gamma outside and re-express things this way. And now I can move the max outside these, the absolute value thing, because the absolute value of the difference in the max of two things is the same as the max of the absolute value of those, of that difference in general. Which gets me here. And now I'm going to introduce, here I'm just taking the maximum over actions, but I'm going to introduce states too. I say, well, what if I looked at the maximum over not just actions, but over states too, as well as actions? Then clearly this maximum will be no more than this maximum. I mean, this is for a particular state S prime. And here, if I allow it to range over any S, I'll call it S double prime. Then I'll have an even weaker bound. But this is the quantity we were claiming that we could prove about. So we were saying that delta n was the maximum error in the table over any state action pair. And that's what we've now got. And what we're showing is that we reduced it by a factor of gamma. Okay, so if you follow through, the intuition of this proof is just showing that because of our update rule, the difference between it and the truth is going to be reduced every time we apply it. Our updated value and the truth are going to get closer every time we apply it, and do so by a factor of gamma. And so after every full interval, we visited every state action pair. That's what we meant by a full interval. And so we've reduced by gamma the worst error that's in the table. And now if we have an infinite number of full intervals, we'll keep reducing that by gamma and eventually get to arbitrarily close estimate of Q.
This proof only works for the case when the reward function is deterministic.
That's true. So this only works, we only covered this when the reward function is deterministic. In fact, the proof you can generalize the proof to non-deterministic reward functions and non-deterministic actions. And it still carries through. Okay, so let's end there for today, and we'll pick up the rest of this next time.